Hey everybody, welcome back to another round of astronomy. Yeah, let's get going. Well, as the title of this slide would suggest, we are going to introduce a new model today called the Ptolemaic model. Now, this model is still geocentric, Earth-centered, and it aims to address some of the issues that we see in the celestial sphere model. Question for you. When does scientific knowledge progress? You got it? Yeah, good. And don't forget, you pause those videos, right? This isn't like you're supposed to come up with it in the next 10 seconds. This is pause the video, think about it, and then come back in. Okay, so scientific model. When does scientific knowledge progress? It's when we have a model that cannot explain our observations. And I should be even more specific, right? It's not the model right here that we're thinking about and the previous observations. It is when we're down here, right? We've made a prediction using our model and then find out that that prediction is not borne out by the observations, okay? Right? When did you learn something about this? It wasn't when you first drew the lines in. It was after we started pulling the ropes and finding out that the figure you drew didn't explain some sort of behavior. It's scientific knowledge. Our models get better. Our understanding of reality gets a little bit better when our models fail. That tells us that we haven't taken into account something. So it's like up until this point, the failure point, we are living in our own ignorance. We don't know how bad or how inaccurate our model is. It's only when we finally find a failure that we realize our own ignorance, and then we can improve. Okay? Good. Okay. So let's go ahead. Recap on the last model. We are dealing with the celestial sphere, and this comes to us from the ancient Greeks. Again, I'm highlighting it is geocentric. The Earth is in the center of the universe. Okay? And all of the stars are the same distance away. Now, on a previous lecture, we left with the idea that if the I shouldn't say if, I should say according to the celestial sphere model, we have that all of the objects move in the same direction, and they should all move at the same speed. In other words, a single star should sweep across the sky, moving the same way all the time. Okay? Once you see the star sweeping across the sky, it always is staying at that rate. Okay, those are predictions. We can go out and start making observations about that. So here's two pictures that I'm going to put up for you. Okay? Now these two pictures are taken at the same time of day, say 2 days apart, or a day apart. So I take this picture at 8 o'clock, and then I take this picture at 8 o'clock 24 hours later. Okay. Now that in reality, these are a couple weeks apart, but it gets the idea across. Okay. So here's the question I have for you. What changes? You see it? Yeah, good. We can sit here and we can compare these two photographs and we see that something changes. Right? You see, actually it's right here, this bright spot, not the pointer, but it's just above the pointer. You see that bright spot now has shifted to a new location in the photograph. So wait a minute, we've already need to modify our celestial sphere model a little bit. We have some objects that don't move at the same rate as the background stars. Okay? So what do we do there? Well, the ancient Greeks said, okay, we know there are a couple of stars that do not appear to move with the background stars. So what do we do about those? What we are going to do is we'll say, fine, we are going to not have one celestial sphere. We will have a couple of spheres. We are going to put the Earth at the center still, and we'll have our sphere that contains the background stars. So I'll put some stars here, just like we drew. And these very special wandering stars, what we're going to do is we'll place them on their own separate sphere. That sphere is still centered on the Earth, and rather than containing a bunch of stars, it just contains one. And as it turns out, that's fine. Okay? The ancient Greeks knew about 5 of these wandering stars. In fact, I believe the ancient Greek word was called plana, literally means wandering star, from which we get the term planets. Okay. Now another term for you, we'll put this in here. Okay, let me get rid of that, is the term prograde. So I've put some cardinal directions here. I've said, okay, well, if you pretend that you're facing south, that means east is to your left and west is to your right. And I will give you the definition of prograde motion. Okay? It is the apparent shift of an object's position from west to east. What that means is that if you go out tonight at 8 o'clock, let's say 8 p.m., and you look at the object, and you go out the next day at 8 p.m., you will see that the object has shifted to the east. There are 2 objects that will always follow prograde motion. And in fact, I believe this is where the term comes in. So go out, start looking for this, but one of them is the moon. Go out tonight, observe where the moon is. Take kind of a bearing with respect to the horizon. If there's any notable features, the cupola of Donner Hall or Parker Auditorium or, something. But go out tonight, take a look at the moon, look at your watch, make sure you know what time it is. Okay? Then the next day, go out at roughly the same time and look again. Okay? You'll notice that the moon has shifted to the east with respect to the background stars. Okay? Now, for completeness, you also have what is called retrograde motion. Okay? And that is where we're going to get into a bit of trouble. Remember, the celestial sphere model, even this modified one, where we've taken into account the motion of the planets, that would still suggest that the spheres rotate in the same direction at a constant rate. That means that even though the planets move at a different speed than the background stars, planets should always move in the same direction, okay, at the same speed. So what I have for you now, let's go ahead and take a video. It's a series of overlapped images. This spans a couple of months, if I'm not mistaken. And I'll go ahead and just play it for you once or twice. What do you notice? I'll play it again. Uh-oh. We've got a problem. These were taken at the same time of day, several days or weeks apart, and we have a problem. You notice that initially this wandering star undergoes prograde motion. It starts out somewhere down here, and it slowly, this is again the south, excuse me, that's a terrible color. Let's go ahead and do something like this. This is still east, this is the south, this is still west. Our wandering star starts out somewhere here, and it starts undergoing prograde motion. It goes day after day towards the east. But then at some point, you notice, number one, it slows down, right? It stops moving at the same rate. And number two, worse than that, eventually it stops and it starts undergoing retrograde motion. It starts appearing to shift to the west night after night after night, right? That completely, right? What happens when you have an observation that conflicts with your model's predictions? What do you have to do? Yeah, we have to modify the model. We realize that our model is not accurate. It's not complete. And so it does not pass. We have to refine the model to incorporate our new observations. So how do we modify our celestial sphere model to take into account the retrograde motion of planets? And I'm completely confident that the ancient Greeks knew that there was a problem with their model. Okay? The issue is that they didn't have a good solution. They said, I'm paraphrasing, we know that our model's not 100% accurate, but we don't have the creativity to come up with a better model. Okay? That's where Ptolemy steps in. Ptolemy introduces just a slight change. Rather than the wandering planets, and I have Venus displayed here, rather than Venus being simply on a celestial sphere, okay, Ptolemy says, I am going to make a small change. I am going to pretend that there are, for lack of a better word, I'll say 2 spheres. Venus lies on a small sphere and runs around the small sphere, and the center of the small sphere runs around the larger sphere. So you have 2 motions going on. Venus goes around the small sphere, while the center of the small sphere goes around the larger one. Now we should ask ourselves, how does the Ptolemaic model address the issue of retrograde motion, right? When you construct a new model, you also need to take into account these new observations that your old model failed to predict. So how does the Ptolemaic model take care of the observation of retrograde motion? Well, when Venus is on the top side of the smaller loop, it is moving to the left-hand side. That would be, as viewed from Earth, the prograde motion of the planet. Whereas on the bottom side of that small loop, Venus will be moving to the right of the screen, and from Earth, that would be a retrograde motion. And so now we have a way of sometimes seeing retrograde motion and other times seeing prograde motion. Now, all the ancient Greeks, or Ptolemy, I guess this is now around the 1st century, something like that. Okay. Now all we have to do is go out and observe and see how often Venus undergoes retrograde motion. That will be indicative of how quickly it runs around this smaller sphere. Cool, huh? Yeah. So let me go ahead. Let me give you 2 more terms that are associated with the Ptolemaic model. I keep saying the small sphere and the large sphere. We don't usually use those words. They are usually referred to as the epicycle and the deferent. So the larger sphere would be called the deferent, okay? The orbit of the planet around the sun. Okay? And then the smaller sphere would be the epicycle. So generally when you hear the Ptolemaic model, It is the introduction of epicycles to the geocentric model. Okay? That's really Ptolemy's huge contribution. It's this epicycle, the second sphere, the smaller one, that helps us describe the retrograde motion. So what do we have here? Let me walk you through first. In the center here, right here, we have the Earth. Okay? Then, as we move progressively outwards from the Earth, there's just a tiny little sphere there, which is the Moon. And then this bright spot, Venus. We have Mercury, then the Sun. And then we move further out. Mars, notice it's colored red. Then we have Jupiter and finally Saturn. So this is the entire universe of the ancient Greeks, right? The universe is essentially the 5 planets, the moon, the sun, and the background stars. Okay. Now you'll notice as well that each of the planets, or maybe I should be more general, objects, each of the objects has both an epicycle and a deferent. Okay. So the only two that do not have an epicycle are the sun and the moon. This is just to give you an idea about kind of how do I visualize this. So again, each of the planets is going to run around their epicycle while the center of the epicycle follows the deferent. And it'll do kind of a trace for each of the planets. So you'll kind of see the combined motion. So already we're using this idea of making observations to refine our models and get better. Okay? Good. Okay. Just like the celestial sphere model, the Ptolemaic model also needs to provide some sort of predictions that can be used for future observations. So I'm going to introduce a couple of ideas here and probably the following lecture, and we're going to use both of those predictions to move forward in building a better model. So here's the first idea. If you go out tonight and you observe Venus, okay, so here we definitely need to use Venus. I'll circle it right here. Okay? So if you go out tonight and you observe Venus and you point at Venus and you point at the sun, okay, the angle between your two arms, okay, will never be greater than 48 degrees. It doesn't matter what time of day, it doesn't matter what time of year, go out and try this. It'll probably take you somewhere around 400 days to make the whole observation. Okay? Of course, maybe even longer than that because you should do it twice to make sure it's actually a pattern, right? Not only one observation is not good enough, you should make sure that you see a pattern. Okay? So maybe it'll take you 3 years to do the whole observation. Okay? But if you go out night after night, point at Venus, you point at the sun, you measure the angle between your two arms, and you do that for long enough that you see the pattern, you will notice that Venus is never more than 48 degrees away from the sun. The angle between your two arms never exceeds 48 degrees. That's what astronomers refer to as the maximum elongation. If you go and look it up, it turns out the maximum elongation of Venus is 47 degrees, 33 arc minutes. I'll just round it to 48 degrees. That's good enough. Okay. So, what that means, I'll ask you the question. Okay? The fact that Venus and the sun are never more than 48 degrees away from each other. Okay? What does that imply about the motion of Venus and the sun along their respective deferents? Go ahead, take a minute, see if you can hack out an answer. You got it? Yeah, good. And I have a drawing here on purpose for you. right? So I have Venus and its epicycle and its deferent. I have the sun and its deferent. And the idea, if I'm standing on Earth, I point at Venus and I point at the sun. They're never more than 48 degrees away. That means that as the sun travels along its deferent, Venus must be traveling roughly the same amount along its deferent. So the maximum elongation tells us that Venus and the sun travel roughly together along their respective deferents. Hang on to that idea. Okay? This is how the Ptolemaic model explains the maximum elongation. We are going to need to take a slight byline in the next lecture to work on some more terminology. And then we'll return, take this idea, the maximum elongation, and the next idea, which is called the phases of Venus, and we're going to put those two together. And that will give us an idea of a new revolution in astronomy, a new model that is completely different than the old models. So stay tuned. Exciting times ahead. Hey, thanks for your attention. Keep up the good work. I'll see you next time.